think we should get started. Hello, everyone. Um, well, we are doing this class remotely because I have to come to India last minute for some medical procedures. Like, I should be back in 2 weeks. So today's class and next week's class is going to be through Zoom. Okay. So before we begin, few quick logistics um, in terms of the assignments, right? Like, so I assignment, I think assignment three is released, right? Like, so assignment three is released, and um, Kaggle competition is also starting today. So by this time, like, you should have formed your teams, and the data will be released today, and you can start participating in the competition as soon as you have the data. Like, so one important thing to note is you can only make 2 submissions per day. Okay, so I highly encourage you to plan those 2 submissions. Like, just make sure that you don't overfit to the leaderboard that you're seeing, because what you're seeing is the public version of the leaderboard, but your scores are going to be based on the private leaderboard, which will be revealed only after the competition ends. Okay, so don't overfit too much to the public public leaderboard. At the same time, like, try to do more interesting explorations of ideas. Is that clear? Any questions about Kaggle? Any questions about Kaggle? Okay, so so I think somebody is saying that the questions are not available in the website for assignment 3. So the TA has released the assignment 3. You should have received an email with the link to the questions and code. Okay, so we will put it in the website. So sorry, I think the website is not updated, like, simply because I had to travel right after the midterm, and I will hopefully update everything in the website today, tomorrow. Okay, and in terms of the midterm, I hope you did your midterms well. Like, so we will grade it as soon as possible so that we can give back the results in a few days. Okay, so I think some of you asked for the results to be released before the ad drop deadline, or the dropping deadline. So we will try to do that. And now that this is almost 9th week of the course, right? Like, so we are getting closer to the finals. Well, we just finished the midterm, but like, we're getting closer to the final, and like, few quick announcements about the final, right? So for the midterm, I did not allow you to have cheat sheet, but for finals, you are allowed to bring one cheat sheet. Okay, so this is going to be one A4 size paper, and both sides is okay. Like, you can write in both sides. So the most important point to remember is this has to be handwritten. Okay, you cannot type or write it in your iPad and then print it. So it has to be handwritten cheat sheet, and you also have to turn in the cheat sheet with the exam paper. So whatever cheat sheet you're bringing to the exam, like, you have to submit it with the exam paper. So if you want a copy of your cheat sheet for yourself, like, take a picture or take a Xerox before the exam. Okay, so you cannot bring it back after the exam. So just make sure that you have a copy for yourself if you want one. And historically, like, many students have told me that like, this cheat sheet helps a lot in learning, in the sense, like, when you start preparing for the exam and write things in the cheat sheet, this is really a good way to distill the knowledge that you have obtained in the class, right? So use this as an exercise to summarize the lectures and try to use it wisely. Okay. At the same time, the cheat sheet should be only there for reference. Like, so if you plan in such a way that like you have to absolutely look at the cheat sheet for solving questions, you will not have enough time to solve the questions in the exam. Okay, so you should still prepare in such a way that you can answer the questions without cheat sheet and use the cheat sheet only when it is necessary. Is that clear? Any questions about the final? So if you have any questions, like please unmute yourself and ask your questions. Well, it's just very hard to interact via Zoom, so no questions about.
How long?
Yeah.
So is the exam from the start of the course or only for after the?
Yes, it's all the 13 weeks.
Okay, thank you.
And I will release the last 2 years final exams for reference so that you already have the midterms for reference, but I will also release the last 2 years finals for reference so that you have like more questions to practice. Any other question?
Will the exam be an hour and a half like the midterms, or is it gonna be longer?
Sorry, what?
I ask, is the exam's gonna be an hour and a half long or longer?
No, it's going to be 2.5 hours.
Okay.
Okay, so let's get started. Okay, so can someone tell me like what we discussed last week? So what we look at last week? Yeah. Anyone can unmute yourself and tell me what we did last week. Yeah. Is someone answering? So what did we do last week? Okay, I think people are posting in the
Last
chat.
week
Yeah.
we talked about the different metrics like precision, recall,
Yeah.
and F1 score.
Yeah.
And we also start to talk the confusion matrix and the decision trees, I believe.
Yes. So we looked at the evaluation metrics, then we also looked at decision trees, right? Like so decision trees were a bit different from the algorithms that we have seen in the past. In the sense, most of the machine learning algorithms that we have seen in the past are mathematical models where like you give a vector as input and you're basically getting some value out of the model, right? Like it's like an equation that you implement, which takes some vector as input and produces the predictions, right? Like on the other hand, decision trees are more symbolic in the sense like you actually construct a tree with a bunch of test conditions like that you follow to reach the root of like to reach the leaves of the tree, and like in the leaf you have the decision, right? Like so we talked about how decision trees are interpretable, like how they can make nonlinear decision boundary and all those things. So can someone tell me if decision trees are generative models or discriminative models or discriminant based models? Like what kind of classification algorithm is a decision tree? Anyone? Well, you could also post your answers in chat if you want to, right? But I would like to see more interactions. This is a Zoom class, and like I really want people to unmute themselves and answer. Also, please turn on your video if you can, right, so that we can see you. So someone, okay, so in the chat, Clemens is saying it's a discriminant model. Any other answers? Anyone else? So Clemens, can you unmute yourself and tell why this is a discriminant model? So why is it a discriminant model? Any other answers?
So we are not using any probabilistic approach.
Is that true though? When you're going all the way to the root, how do you decide the class value? Like when you go all the way from the root to the leaf, like how do you decide the class value?
With the entropy?
Yeah, so you have some notion of
Yeah,
probability,
okay.
right?
But, yeah, okay. But you're not calculating P of y given x or P of x given y.
Well, you are implicitly calculating P of y given x.
Oh, okay.
Because in a tree, given some input x, you follow the path and it takes you to some node, like the final leaf node, where the leaf node has some, for example, 7 out of 10 classes being yes, right? Then the probability of y given x is 0.7. We just call it an S node, like because the probability is 0.7, right? So in that sense, decision trees are discriminative models. Is that clear?
I wanted to say this decision tree are discriminating model because their focus is more on the boundaries rather
Yes.
than the distribution.
Yes. Yes. So they are discriminative models. Okay. Okay. So that was about decision trees, right? Like, so now for today's lecture, so we're going to focus on, well, not on a specific machine learning algorithm, but on ways in which we could combine different machine learning algorithms. Okay. So specifically, we're going to look at ensemble methods. Okay. Which is basically this idea of combining different machine learning models to form like a bigger prediction system. Okay, so this is kind of extremely useful, especially when you're participating in Kaggle competitions like the one that we just started in the course, right? Like, so because typically ensemble methods help you to get a little bit better performance than what you could normally get with just one model by combining the expertise of different models. Is that clear? Okay, so to get started with ensemble models, right? So I want to motivate this by using the idea of decision trees. Okay, so here you see an example decision tree. Okay, so the individual tests doesn't matter, right? Like, so like the first node is basically looking at some variable x1. There are two features here for this data set, x1 and x2. So the first node is looking at x1, and if x1 is greater than some value theta 1, you go to the left side. Otherwise, you go to the right side, right? Then the second node is looking at x2, and if x2 is less than theta 2, you go to this side. Otherwise, you go to this side. And the same is true in these tests as well, right? So in some sense, this decision tree is trying to take every example that exists and it is trying to put it in the leaves. Or in other words, we are really trying to divide the region of data into different classes based on the way in which we follow this decision tree, right? So, for example, the first test, x1 is greater than theta1, right? It separates the data in such a way that anything that is x1 lesser than theta1 is in one side, greater than theta1 is in another side, right? Which means if this is my data space, x1, x2, then theta1 is separating the data into two parts. Now, when x1 is greater than theta1, then you're looking at x2, right? So that is the division by theta2. So by theta2, I divide the data into A region and B region. Similarly, with theta3, I divide the data again. Then by theta4, I divide the data again. Is that clear? Now, what we have done is we have divided the data space into 5 different regions, A, B, C, D, and E. And typically in a decision tree, like we would give a label by the leaf, right? Like, so for example, let's assume that this is an yes or no problem. Then we can say, oh, just as an example, this is yes, this is no, this is yes, this is no, this is yes, just as an example, right? So given a new data point, all you have to do is follow the tree and identify the region in which the new data point lies, and that will give you the class grade. Let's take an example. Let's say I have a data point which lies in the E region. So what would be its class?
Yes.
Yes, right? Like, so if a data point lies in the E region, then like you would have traversed through the tree like this and you would have reached here. And for E, it is actually yes, right? So the other way to look at this decision tree is you have 5 different regions and each region has its own classifier. So in some sense, there are 5 classifiers. Okay. By the way, nothing stops us from fitting a classifier here instead of just yes. Like, so in this case, like I'm putting a yes. Instead of putting yes, I could have a simple machine learning model which takes all the data that lies in the E region and constructs a classifier out of it, right? Like you could actually have individual classifiers for each of these leaves. Is that clear? So in that sense, a decision tree, when it splits the data into 5 different regions, it's really using 5 different classifiers, right? Like the decision tree has 5 different classifiers, but the only catch here is like they use only one out of these 5 classifiers at a time, right? So depending on which region you fall under, you will use that region's classifier. Is that clear? Any questions? Yeah.
Yeah. My question was, let's say that for each region we have like a simple KNN.
Yeah.
Will it be like will it be like expensive to deploy the decision trees?
Well, if you have a single KNN per leaf, I guess it's going to be a little bit more expensive than running a KNN, right? So, or maybe it might be faster because you are essentially splitting the data into 5 different regions, which means you're going to have a smaller data set for that particular KNN, right? Like, so I would guess on an average, it's not going to be more complex than running a single KNN.
Okay.
It might take a bit more space because you are also constructing the tree, right? But I don't think it's going to be more expensive in terms of computation.
Okay.
Any other question? No questions? Okay, so by this way, we can kind of assume the decision tree can be considered as a group of classifiers where only one classifier is activated, like whenever you have an example, right? Now we can actually generalize this idea. So if I'm anyway thinking about constructing multiple classifiers, why don't I make use of all the classifiers when I make a prediction, right? So the benefit is each classifier could have its own expertise, right? Like so in that case, like you will use the expertise of different classifiers to solve the problem. So the like one way to think about this is like imagine you are trying to solve a really complex problem. Now, instead of doing it as a single person, you have a committee of experts, and they are all trying to solve this problem together. Okay, so that is the idea of ensemble methods. Like, so can we actually construct a committee of different classifiers, each having their own expertise, and we're going to combine all these expertise to get a super classifier or a meta classifier, which is going to have better performance, hopefully, right? So that is the idea of ensemble methods, okay? And the general recipe that we're going to discuss in today's lecture is how to combine multiple models. Right? So this is what ensemble methods is about. Okay. So typically, we're going to assume that we have k different models that we have trained for the given problem. Okay. And each of this model is going to make some prediction t given some input x. Okay, my x is the input and t is the target. Okay, and we are going to denote each classifier as p of t given x comma k, where k is basically the index of the model. Okay, so k is equal to 1 to capital K, which is the index of the model. Okay, now the general prediction that we are interested in, which is p of t given x, is given by summation k is equal to 1 to capital K pi k of x p of t given xk, where pi k of x is equal to the probability of k given x. Is that clear? So what we are doing here is we are combining the prediction of k different models, right? Like each model's prediction is given by p of t given x comma k, right? So we're combining the prediction of k different models, and the way in which we are combining this is by taking a weighted average of all these predictions, where the weight is given by p of k given x. So what is the probability that this is a good model for the given x? It might be the case that given a new example, first and third model are more useful for this example when compared to 2, 4, and 5 models, right? It's out of 5 models. In that case, like you're going to assign higher probability for the first and third classifier and lower probability for the second, third, fourth, the second, fourth classifier. Okay. So this pi is called input dependent mixing coefficient. Is that clear? Any question? Okay, so now we will talk about different algorithms that would combine these models. Okay, so the first algorithm that we are going to talk about, like one of the most popular ensemble methods, is called bagging. Okay, so this was introduced by Breiman in 1996, and bagging is really simple idea. Like all we do in bagging is we train k different models and just take an average of the prediction of all these models. Okay, so bagging basically takes an average. Okay, it averages the prediction of a set of models. Okay, so how do we do that? So to begin with, we have a data set that we want to train on, right? And we are training k different models, and we're taking an average of the prediction of these k different models. Okay, so we start with some n data points. Okay, so where x is given by this one, there are n data points are there. Okay, and similarly t also there is 1 to n, right? So, and the idea here is to train k different models and take an average. Okay, so here is an interesting question. Let's say I want to take the data set and train k different logistic regression models and take an average of predictions of all these models. Do you think it's a good idea to train 10 different logistic regression models with the same data set? Any thoughts? Like, I want to train 10 different models and take an average. Okay, so that is my bagging strategy. Now, if I train 10 different logistic regression models with the same data set, what are we going to get?
Are we just going to learn the same things on the tens
Yeah,
data
I think
sets?
there are also some answers in the chat, right? Like, so Jeremy's answer is correct too. By the way, I really want everyone to speak up. So please unmute yourself and answer the questions, okay? Okay, so Jeremy's answer is correct. Like, so we are essentially going to get the same logistical regression classifier if we are doing 10 different models with the same logistic regression model, right? So it's not very useful idea to back, right? Like, so what can we do to improve this strategy? Like, what can we do to improve this algorithm so that we can actually get 10 different logistic regression models?
Can we split our data into like, let's say we have n models into n different parts?
Okay, that's one interesting idea, right? Like, so you can actually split your data into 10 different parts so that you train one model per part, and then you combine these models, right? Now, what could go wrong with the strategy? Anyone else? So what could go wrong with the strategy?
Maybe by splitting the data, some models will miss some informations. And isn't it something we're looking for? I don't know.
Yes, they are going to miss some information for sure because you're splitting the data, right?
Can
Is
it be
there
like can it be like a data leakage like we saw earlier? Like by splitting the models, is it may be learning the test part for the other model, etc. Like a data leakage.
I don't think there's any data like leakage issue here. So the previous answer is kind of in the right direction, in the sense like when you split the data strictly into different parts, then like each classifier is learning only from one part, which could be a bit limiting, right? Like, is there any way in which we could improve the strategy? Okay, so we'll look at a slightly improved version of the strategy. Okay, so this is called bootstrap aggregation. Okay, so the general idea of bootstrap aggregation is this: like, so we have some data set, let's say a bunch of x1 to n data points, right? We have n data points, and the goal is actually to construct k different data sets from these n data points. Okay, so we want to have a bunch of examples in each data set, And the most important thing is we want some diversity in these data sets so that when we train a model with all these different data sets, like we get slightly different models, and combining these models is actually beneficial, right? So the idea of bootstrap aggregation is actually to construct these k different data sets, okay, where each data set is going to have n examples. Remember, the original data set actually has n examples, okay? Each data set is going to have n examples, okay? The only difference is these are going to be sampled from X with replacement. So what does this mean? Like, so just let's take a toy example, right? Let's say I have a data set which has 1, 2, 3, 4, 5. This is my data set. Okay. Now, to construct D1, I'm going to sample 5 numbers from 1 to 5 with replacement. So which means the first time I sample, I may get a 1. The second time I sample, I might get a 3. Now, the third time I sample, because I'm sampling with replacement, I'm still sampling from all the 1 to 5. So I might get another 1. Okay. The next time I sample, I might get a 4. Next time I sample, I might get a 3. Now that I have 5 samples, I'm going to stop. So this is my data set 1. Is that clear? So now I can also have a data set 2, just 1 second. So I can have a data set 2, which is sampled with replacement. So I could get a 1, I could get a 4, I could get a 5, 3, 3 as an example, right? So I can actually sample k different times with replacement, and each data set is going to be a little bit different from the previous data sets. Now if I train a logistic regression model with this data sets, I'm going to get a set of different models. Okay. There was a question.
Yeah. In the worst case, in this example, could we have like in the, let's say in data set 3, 5 times the same value?
Sorry, can you repeat the question?
You say that each time we sample, we do a replacement, and we
Yes.
could have like the same value. Let's say in data set 1, we have 2 times the value 1. In the
Yeah.
worst case, can we have like 5 times the same value?
Yes, but that's very rare, right? Like the
Okay.
probability of sampling 5 consecutively for 5 times is very rare. Well, also 5 is just an example, right? Like typically your data set is going to have like 1,000 examples or 2,000
Yeah.
examples. So the probability of getting one example 1,000 times is, it's not 0, but like it's very
Yeah,
rare, right? So typically what would happen is if you have 1,000 examples, maybe you're going to have 70% unique examples or 80% unique examples, right? So you would still have enough unique examples, but you would also have some repetition. Is that clear? Okay, so once you have these k different data sets, then you can train k different models and just take an average of their prediction. Okay, so now we're going to do this bootstrap aggregation, but for regression problem. Okay, so what I'm going to do is I'm going to take the data set and construct m different bootstrap data sets. Okay, and for each of these data set, I'm going to train a regression model. And let's say the output of these regression models are given by y1 of x, y2 of x, all the way to ym of x. Is that clear? So once I get, so each one of this is a regression, like a regression model. So this is my first regression model trained on the first data set. This is my second regression model trained on the second data set. This is my mth regression model trained on the mth data set, right? Like so once I train all these different regression models, then I can construct the bagging solution. We are going to call this y committee of x because we have a committee of regression models. And this is basically the average prediction. So it's going to be 1 over m, summation m is equal to 1 to capital M, ym of x. So this is my model. Is that clear? Any questions so far? Okay, so now I'm going to argue that this committee classifier, committee regressor, like YCOM of X, right, is strictly better than using just one regression model. Okay, I'm going to show you that it's going to have lesser error than having just one regression model. Is that clear? Okay, so let's see how that is the case. So let's say h of x is the true regression function. So this is the function that we are trying to learn. Okay, so then I can write ym of x, which is basically each model's prediction, as essentially h of x plus some epsilon m of x, where epsilon m of x is the model's error. If the model's error is 0, then your prediction is exactly h of x. However, models make mistakes, so the mistake is accounted through epsilon m of x. Is that clear? Okay, so now let's look at the average sum of squared error. Okay, so I'm going to talk about average sum of squared error for a single model. Then we will also compute the average sum of squared error for the committee model. Okay, for a single model, the average sum of squared error is given by expected value of ym of x minus h of x, the whole square, right? So this I can write as expected value of ym of x can be written as h of x plus epsilon m of x minus h of x, the whole square. Okay, so the h of x and minus h of x cancels each other, so you're going to get expected value of epsilon m of x, the whole square. Is that clear? So this is for one model, right? So if I want to talk about the average error for m different models, so the E average is given by 1 over m summation m is equal to 1 to capital M, expected value of epsilon m of x, the whole square. Is that clear? So this is just the average sum of squared error for m individual models, right? So now let's actually look at the expected error from the committee. Okay, so expected error from the committee. By the way, it's going to be easier for me to teach if at least some of you have your videos on, so that I can see your face reactions, like which really helps me to understand, like know whether you are understanding what I'm teaching. Okay, because right now it looks like I'm teaching to a wall because everyone's video is turned off. So if someone can turn on their video, I could follow your face while teaching. Okay, so the expected error from the committee, right, is given by ecom. Okay, so the ecom is given by expected error, which is basically the difference between the model's prediction and h of x, the whole square, right? So the model's prediction now, because it is a committee, the model's prediction is given by 1 over m summation m is equal to 1 to capital M ym of x. This is model's prediction, right? Minus h of x, the whole square. Is that clear? Now, this is given by expected value of 1 over m, okay, summation m is equal to 1 to capital M epsilon m of x, the whole square. Is that right? So what I have done is I have substituted ym of x as h of x plus epsilon m of x the whole square, right? So sorry, ym of x as h of x plus ym of x. So h of x will cancel. So you will just get epsilon m of x the whole square. Okay. So now I can bring 1 over m square outside the expectation because it is just a constant, right? So this becomes 1 over m square expected value of summation m is equal to 1 to capital M epsilon m of x the whole square. Is that clear? Okay. So now I'm going to make some assumptions. So I'm going to make this assumption that the error that the model make are zero mean and uncorrelated. So what does this mean? This means that I'm going to make this assumption that the expected value of epsilon m of x is 0. Okay, that is the first assumption, which is a zero mean assumption. The error has zero mean. And the second assumption is the error between two different models are not correlated. Okay, so what does this mean? This means that expected value of epsilon m of x times epsilon n of x is equal to 0 whenever m is not equal to n. Okay, this is actually a very crucial assumption. So here I'm assuming that somehow I magically created k different models or m different models, which makes errors in different situations. Okay, this is when the committee is really useful. The committee is really useful when you have a group of people where each one has different set of weaknesses, so that when you combine them together, one expert's weakness is compensated by other expert's strength, right? Like, so when their errors are not correlated, then whenever the first member is making some mistake, the other members are not making the mistakes, which means when you take an average of predictions, the other member's prediction is going to dominate. And if you're, for example, taking a max, right, in majority voting cases, if there's only one mistake, right, like the remaining is all correct, so you're going to make correct prediction, nonetheless. Is that clear? So with this assumption, okay, I can rewrite this as 1 over m square summation m is equal to 1 to capital M, summation n is equal to 1 to capital M, expected value of epsilon m of x, epsilon m of x. Okay. So all I have done here is I have expanded the summation. So there was a summation epsilon m of x the whole square. I am just expanding that, right? So now I'm going to make use of these assumptions. So the assumption says that whenever m is equal to n, right? So the expected value of epsilon m of x is 0. And whenever m is not equal to n, things are uncorrelated. So I can kind of write this as ecom is equal to 1 over m square summation m is equal to 1 to capital N expected value of epsilon m of x whole square. Okay, so this can be written as 1 over m expected value of the average prediction. Is that right? Because you see here the average error for m different models is given by 1 over m summation m expected value of e m of x the whole square. So there's just one extra m here. So ecom is equal to 1 over m ER, right? In general, the error made by the committee is always less than or equal to the error, the average error of k different models. Is that clear? So this is interesting because this basically says that instead of training one regression model, if you train k different regression models or m different regression models, then your error is going to be m times lesser. So what is the catch here? If this is true, then I could just train 100 different models and I'm going to get 100 times lesser error, right? Like this sounds like almost a loophole because I can just keep training more models and take an average and I would strictly get better performance. Is this true? Is there any catch? Anyone? So look at the argument, right, that we have here. Is it always the case that every time I add more regression models, like my error keeps reducing? Any thoughts? We can also make same arguments for classification, by the way. Okay, so even in classification, we can say that, oh, if I keep adding more classifiers to the same data set, my error is going to keep reducing. So in theory, I can just bring down the error close to zero, right? But we would have solved every machine learning problem this way. So what could go wrong here?
But isn't there like a risk of overfitting?
The risk of overfitting. How would you overfit?
Like if the bias is really low and the error.
Well, if individual, let's say that the individual models are good,
Okay.
right? Because we are doing our best to train these models, right? Let's say the individual models are good, they are not overfitting. Then what could go wrong?
Well, if you have a lot of models, you have more examples in your data set, so the data sets will become more and more similar, so you'd have the exact same model for every single one.
Yeah. So if you have lots of models, there is only so much you can do by sampling with replacement with the data set, right? Like you are still having a finite data set from which you are sampling, right? So what would go wrong is this assumption would get violated. So the assumption that the errors of these models are not correlated will get violated. Okay, so the models are going to become more and more correlated. When they are more correlated, then this whole thing is not going to be always the case, right? So which is why I put a less than or equal to here, like which means you will reduce the error by adding few models, but after some point, the benefit of adding models become lesser and lesser. Okay, so after, let's say, k different models, you're going to start adding models. These models are going to look very similar to the previously added models, which means they're going to have very correlated prediction when compared to the previous model. So there's less diversity in prediction, and hence no big benefit in adding more models. So which means there is actually a limit. Like so, you can reduce your error by 5%, for example. You cannot reduce your error by 50% or 80% by just doing bagging. Is that clear? Any questions so far?
Are they also going to share the same inductive bias?
Can you repeat your question?
Like they all share the same inductive bias, right? This is the same model.
Okay, yeah, that's a good point. So far, we are talking about bagging same models, okay? Simply because it is just easier to take an average of all these models, right? But maybe after the break, like we will talk about like how to combine models when they are not sharing the inductive bias. Is that clear?
Yeah.
So for now, like we are just considering how to bag different models, which are all same type of models. For example, like bag just logistic regressions or bag a bunch of decision trees, etc. Okay, so now let's talk about decision trees, just because we have looked at them last week, right? Like so how do we bag decision trees? But I'm talking about decision trees partly because this is actually the context in which bagging was introduced originally. Okay, so what could go wrong when I bag a bunch of decision trees? So I'm doing bagging. So I have a fixed data set and I'm doing bagging with a bunch of decision, like I'm just bagging a bunch of decision trees. So what could go wrong? Any thoughts?
Isn't decision tree already a form of bagging since we just take the different models on the
Not really, right? Like, because in decision tree you are still using one classifier at a time. Like also typically we don't fit classifiers in the leaf for decision tree, right? Like it is just yes or no. So the problem with decision trees is they actually are going to generate highly correlated trees. Okay, so if you simply bag decision trees, then the generated trees are highly correlated. So why is that the case? Like, it's just that if you're just making small changes to the data set, this is not going to affect the tree structure significantly. Okay, because the tree is constructed based on the algorithm that we discussed last week, right? Like where you try to find the most like discriminative feature to test on, and you continue this, right? So this structure or the sequence of tests is not largely affected by just changing a little bit of data set. Is that clear? So in the context of decision trees, right? So what Brayman introduced, like as a variation of bagging, is what people popularly call as random forests. Okay, so this was introduced by Brayman in 2001. Okay, so the idea of random forest is, again, we're going to start with K bootstrap data. So this is bagging technique. So we're going to start with K bootstrap data sets. Okay, now to avoid correlation or to break the correlation among K different decision trees, what I'm going to do in each node is I'm going to pick only M variables at random, and I'm going to consider the best test out of these M random variables. This M is typically much lesser than the number of features that you have. Is that clear? So I'm following the same decision tree process. It is just that instead of considering all the features to construct the root, I'm going to consider only a subset of features. And I repeat this process. In each node, I'm just going to pick a small subset of features that I'm considering to pick the test. Okay, and the other important change is I'm not going to do any pruning, so no pruning. Okay, so when you don't do any pruning, you're going to overfit, right? Interestingly, this is going to create K different trees, where each tree is going to have low bias because there is no pruning and very high variance. Okay, now because I picked different variables to test for different trees, these variances are not going to be correlated. So, or in other words, like what random forest is really trying to do is to construct a forest of trees, right? And so you have different trees, each having low bias and high variance. Now, because I bag these trees together, and we have seen previously that bagging reduces the error, right? Like, so in some sense, the bagging reduces this variance. So the end result is I get an algorithm which has both low bias and low variance. Is that clear? So this is very interesting. This is probably the first algorithm that we are seeing in this class, which has both low bias and low variance. Okay, individual tree has low bias and high variance. But when I put a bunch of low bias, high variance trees together, right? Like so then we get a committee or a random forest which has both low bias and low variance. Is that clear? Any question? Okay, so we will just do one variation of this and then we'll take a break. So we're going to look at another variant of random forests, which is called extremely randomized trees, or ERTs. Okay, here we are again going to have k different bootstrap data sets. Now in each node, right, we're going to pick m features at random, just like random forest. We're going to make one more change. So the change here is for each feature, I'm going to pick a random test for each feature. Okay, instead of considering all possible tests and use entropy or some other measure to pick the best test, right? I'm just going to pick a random test for each feature, and then I'm going to compare these different random tests and pick the best out of it. Okay, so the depth of the trees is a hyperparameter here. So we are not going all the way to the end. We will prune, but then the depth is a hyperparameter. Okay, so in some sense, extremely randomized trees are even more even more random when compared to random forest. So which means you're going to have even more variance, and like you're going to reduce this variance by just boosting, like bagging a bunch of trees. Is that clear? Any questions so far?
I didn't understand that last part with the extremely randomized trees.
Okay, so with so the main difference between ERTs and random forests is like in random forest, you're just picking m variables at random, right? But for each of these m variables, you're going to consider all possible tests, and you would just pick the best test, right? So the difference here is instead of considering all possible tests for all these m features, like I'm going to pick a random test for each of these features, which means if I have m features, I'm going to have only m different tests, and I'm going to pick the best out of these m different tests.
Okay, thanks.
Any other questions? Okay, I think that concludes our discussion on the idea of bagging. Yeah, Jeremy?
Yeah, I was wondering where's the catch here, because it seems
Well, the catch is you will still have diminishing returns after X number of trees. Like you could add 10 trees, 20 trees, 30 trees. Like for a fixed data set, you cannot just have like too many trees, right? So you will still end up with like diminishing returns after some point. But the benefit of random forest on extremely randomized trees is you will start seeing the diminishing returns only after a large number of trees when compared to simple random forests, like when compared to just bagging a bunch of trees.
Okay.
Is that clear?
Yeah.
Any other question? Okay, I think we will take a break here.